Thank you, Andrew. Good morning. Like the title says, and as Andrew introduced, we're interested in the ion precipitation at the poles of the moon, and we've used data from the Kaguya mission to better quantify the ion fluxes there. There are several different motivations for our research. In particular, we want to understand implantation of volatiles. This from ion impacts, this will mostly come from protons, but there's also helium, as well as oxygen ions, oxygen mostly then from the ion outflow of Earth. And they can increase volatile deposits in the permanently shadowed regions. They can also contribute to water formation, even though it's more like a multiple-step process, as Tom Orlando talked about yesterday, for example. And on the other hand, we can also have sputtering of ices. So there's also a component of erosion and therefore depletion of volatile deposits. And to better understand all these effects, we need a quantification of the ion fluxes that are actually able to impact the poles and specifically permanently shadowed regions inside of larger craters. Now, there have been several studies for this. I show an example here of a numerical study by Rhodes and Farrell a couple years ago that showed how a parallel flowing solar wind can reach craters by electric fields that are generated due to a bigger mobility of the electrons. And there is also studies from the data side by Nino and Poppy here from analysis of the Themis Artemis mission that showed that you have large populations of non-ecliptic ion fluxes when the moon is in Earth's magnetotail, where you have hotter plasma populations. Now, as the animation shows here, the Themis Artemis mission has some drawbacks if you want to get direct quantification of polar fluxes, mostly because the orbits are largely in the ecliptic plane. So you don't get any direct flyovers over the poles, and you have to extrapolate polar fluxes from measurements further away from the moon. Now, in order to build on these Themis Artemis measurements, we have now looked at data from the Kaguya mission, which was orbiting the moon for about 2 years between 2007 and 2009 at about a 100-kilometer altitude polar orbit. It also has one ion instrument that has mass resolution, which is not the case for Themis Artemis. So it's an additional advantage that we can use here to expand previous studies. To go into more detail about the instrumentation of Kaguya, it has two ion instruments shown here in yellow and blue. In yellow, it's the Ion Energy Analyzer, or short IEA, which allows us to resolve direction and energy of ion fluxes. And due to the orbit of the mission, IEA is always pointed away from the moon. So it's nice for studying direct precipitation of ion fluxes that then impact the lunar surface. In the data analysis, we found one drawback, that there is a hardware side attenuation of some energy, specifically below about 2.4 keV, to better resolve the maximum of the solar wind, but that ultimately also leads to a lower sensitivity. And we had to fill in some of the bins by reconstructing solar wind fluxes from Omni parameters, or parameters from the Omni data set. But this turned out to work quite well by combining these data. In blue, there is also the Ion Mass Analyzer, a second instrument. And as the name tells you, this is also additional mass resolution with a time of flight addition in the instrument. And it is always pointed towards the moon. It sees a lot of spotted ions, reflected ions. Getting out the direct precipitation can be a bit more challenging due to the viewing geometry. Now, as only limited time, I'm going to focus on measurements with the IEA, the one that points away from the moon. And the way that we get ion fluxes on the lunar surface is by tracing them, taking into account the magnetic field that is measured by Kaguya, as well as the solar wind convection electric field. And even though it's a low altitude orbit, so the high energetic particles are almost on straight lines, but still for the lower energy ones, the gyration needs to be taken into account to get the position of impact properly. We look at data from all of the time of Kaguya in the solar wind as well as in Earth's magnetotail, and we can get these nice precipitation maps for the lunar surface. Now, the coordinate system is chosen here so that in the center you have the subsolar point, here shown in black. So the point on the lunar surface that is always pointing towards the sun, and evidently there you have a much higher ion flux than on the night side, for example, or also on the polar region, specifically North Pole, South Pole. You can see how the fluxes look like there. Looking at the energies of the impact fluxes at the region around the subsolar point, you can see quite a broad spectrum with maximum corresponding to the maximum of the solar wind energy that obviously varies a little bit over the time. And if we look at the North Pole in blue and the South Pole in orange, we get curves that have a somewhat similar shape with the same peak region. There's also almost identical for both of the poles, but generally they're about 2 orders of magnitude lower in around the maximum. What we can also get from the Kaguya dataset is nice information on the impact angles. You can see the animation cycling through different impact angles in reference to the surface normal. And you see this ring developing outwards for the higher impact angles. And this is simply because of the beamed nature of the solar wind, where you have a strong correlation of impact angle and location on the lunar surface, specifically the distance from the subsolar point. But you can also see in as almost a background, the broader impacts from hot to plasma populations that will mostly happen in the magnetotail. Now, what we can do with this to get more information on local impact fluxes is we put our flux data into a ray tracing code that also takes 3D images or 3D models of the lunar surface from LRO LOLA altimetry. And I can show one example here, what this looks like, where we have a model of the region around Shackleton crater on the South Pole. And the color denotes the impact fluxes from our ray tracing that is fed with the Kaguya data. And we can see these nice local contrasts. In yellow, you have higher fluxes on some slopes or on the crater rim of Shackleton, where there is easier access for the essentially parallel flowing solar wind. Evidently, the fluxes are lower inside deeper craters like Shackleton. But as you see in the color bar, the darkest purple is still 6% of the maximum flux here. So
2 minutes.
While we have a reduced flux, there is not a complete shadowing of ion impacts happening. And this is something that is also supported here from our Kaguya data analysis. Now, to conclude my presentation, we looked at data from the Kaguya mission to get better insights into fluxes into the lunar poles that allow us to make these nice precipitation maps where we have information on impact locations, impact energies, and also impact angles. And we can combine this with 3D models of the lunar surface to really get localized information on ion impacts. And in the future, we want to better characterize the ion environment that will be seen for Artemis 3 landing sites, the Viper tracks, or potential future lunar bases. Thank you very much for your attention.
All right, thank you, Paul. We have time for about one question or so. And admittedly, I can't see what's in the room.
Hey, Paul, I have a question about is it possible you can resolve a high spatial resolution to individual PSRs?
I would say so a little bit. There is some limitation for the data because there's about 2 years of mission time, and one drawback of the low altitude orbit is that you at the same point you only get a small region of the moon. So the number of observations per location can be a bit limiting, but I would say there is still enough data to increase the spatial resolution more. Yes, that's
great. Thank you.